Okay, so I think we can start. Um, Welcome everyone for this new series of seminars, talk in the engineering digital community. We are very happy to kick off actually the ninth series, I believe, ninth edition. And today we have, do you see my slides? Okay, so today we have talk from Paula, and we already have another one actually confirmed in about a month from Gabriel Tense about model-driven optimization of process digital twins. But for today, let me introduce our speaker today. We are very happy to welcome Paula Muñoz, and she's PhD candidate at the University of Malaga in Spain. She's actually finishing her PhD, wrapping up her PhD. And she has worked a lot actually in conceptualizing and validating validation step of digital twins with a bit of focus on the fidelity envelope, how to define, how to measure the fidelity of the digital and the physical twins. That's what she's going to talk about today, a bit in more details. And she has also worked a lot on in parallel on uncertainty and model-based software engineering topics. Paula, we are very happy for you for having accepted to give a talk in the EDT seminar, and you're going to talk about how faithful are my digital and physical twins. So, Paula, again, thank you very much for accepting, and the floor is yours. I will let you share your slides,
Perfect.
and you can have it.
So thank you for the warm welcome. And now, are you seeing my slides? Right?
Yes, I can see it.
So
Very well.
good afternoon or good morning, everyone, depending on the part of the world that you're in. In Spain, we just had lunch, so that's the sleepy time of the day. But I hope that you enjoy the talk and that we can have some great discussions about fidelity afterwards. And today, as Jamal already said, I will be presenting a mashup of all the research that I've been doing these past few years, and that it will become my thesis in just a couple of months. But none of this would have been possible without the help of my thesis directors, Antonio Vallecillo and Javier Troya, and also my co-author Manuel Wimmer. And with no further ado, let us begin. So I'm gonna start from the very beginning because I know that we have some disagreements in the community about what a digital twin is. So I want us to be all on the same page so that when I say digital twin, we all know what I'm referring to. So a digital twin, according to the Digital Twin Consortium, is a digital replica of a system, which we call the physical twin, that is synchronized at a specified frequency with a certain level of fidelity. So our keyword is already here. And although some authors define the digital twin as the entire system, including the services and the connections, to the whole system, we call it digital twin system. And this includes both the replica, the physical twin, the services, and the connections. So why is fidelity relevant to digital twins? Why are we using this word? So let's go back to the beginning and let's talk a little bit about history. So as many of you may know, the earliest application of the digital twins began at NASA when we were trying to reach the moon. So at this time, the twinning involved using physical replicas of spaceships that we were sending to space. And the synchronization was done manually to perform what-if scenarios on Earth, just to protect the astronauts. They were performing the decisions first with a digital twin to ensure that these decisions were right. And then they provided the best possible advice to the astronauts. At the end, any errors on the space could be deadly for them, so it was very important to try everything on Earth first. But as time went on, this replica turned virtual using simulations and models, and the synchronization became automatic. And that's are the kind of digital twins that we are dealing with today. But all this story led to one core idea behind digital twins. And that's that we are taking advantage of the replication of an existing system, either to reduce costs, to protect the actual system, or to jump to the future by performing what-if analysis. And this replication is what is bringing us to the concept of fidelity. So now that we know this, what is fidelity? So if we go to the dictionary, we take that the fidelity is the quality or state of being faithful. This definition is not really helpful. So let's go to faithful. And it means true to the facts, to an standard, or to an original. Therefore, based on this, we want a counterpart that is true to the original. However, a perfect model that replicates every process or characteristic of a physical system is completely unfeasible, because this would require not just reproducing the structure and behavior of the real-world elements, but this would also require to model every interaction with a possible unpredictable environment. For example, if we were to create a digital twin of a human, we'd need to replicate every cell, for example, in the skin, and its interaction with substances, radiations, and temperature. And that would be just the skin. We need to model for every other organ and also the interactions between each organ. And this would lead to complex models interacting with one another. And even then, we couldn't be sure if we capture all the emergent behaviors. So such models also would be computationally expensive and at the end, impossible to build. So we are leaving behind the definition by the dictionary, and let's focus on a definition created by engineers. So our definition of fidelity is the degree to which a model reproduces the actual state and behavior of a system in a measurable way. So now we are talking about degrees, because absolute fidelity is unfeasible. And to manage the complexity, we generally use two mechanisms: resolution and abstraction. And now I want to introduce you to the interplay and the relationship between abstraction, resolution, and fidelity. So the level of fidelity of a model is determined by the level of abstraction and resolution. So what is abstraction? Abstraction is the process of selecting the essential aspects of a system which we want to represent, and ignoring those aspects that are not relevant for the purpose. And on the other hand, resolution is the level of detail used to represent these aspects. So we need to do both. Select the important elements and then define the level of fidelity of the elements that we select. So if we go back to the example of the human digital twin, and if, for example, we are doing a model of the skin, but the purpose of this system is to simulate acne. In this case, we can abstract most of the organs and focus solely on the skin. But we might even ignore external factors like the sun, radiation, and unless, of course, we are studying, for example, the effect of radiation on acne scars, for example. But when it comes to resolution, we could select how frequently we want to update our model. So if we want it once an hour or once every 2 days, depending on the level of detail. So where do we come with this? So it's not just about the number of elements and the resolution, it's about how this element and this level of detail affects the purpose of the system. So any model, even a digital twin, must have a purpose. And so if we leave out elements that aren't relevant to the system purpose, we are not really lowering this level of fidelity. The system fidelity is tied to this specific purpose. So the purpose needs to be as clear as possible and to be as specific as possible so that we can figure out exactly what is really necessary and what are the boundaries of the purpose of our system. And now let's go back to another example. For example, if we want to improve an elevator's behavior, for finding the best strategy for picking up passengers, we have many elevators, they are calling for the elevators, and we want to have the best possible strategy for this. So we would only need a kinematics simulation that would only tell you the time it takes for every elevator to go from one floor to another. But in other example, and if we wanted to predict how the equipment will degrade over time, a basic kinematic model wouldn't be enough. and we need a more detailed dynamics model and some degradation model for every part of the elevator. So in this case, we include new elements to account for the physics and the degradations, depending on the element. And this second model would be more costly, and we would only use it if we were calculating in component degradation. And what do I want to go for with this? So combining these concepts, combining resolution and abstraction, we arrive at multi-fidelity. This means that we can use different models for different parts of the system, each with its own level of fidelity. This flexibility allows us to build hierarchical compositions that adapt to our specific needs. We might use a dynamics model to look for equipment degradation and a kinematics model for scheduling. And even with those, we could have different levels of details, different dynamics models and different kinematics models with different level of details. And so we could use a more detailed model for dynamics that consider lots of elevator parameters, or just a simple one that is quicker and less precise, but also defines dynamics. So you don't always need to have the most faithful model. You just need to have one that is good enough for the task that you want to accomplish. And with all this introduction about abstraction and fidelity, now let's go to the big part. So how do we measure the fidelity of a digital twin? This is based on the one novel approach that we were developing together with Manuel Bimer and was just accepted for publication on TSC. So if you are interested, you can go check out. But don't worry, because I will break it down for you in just a moment. So wait a bit before you dive down into the paper. And let's go back to the elevator example. Today is all about elevators. So to help explain our approach. In this case, the purpose of this system is monitoring the dynamics of the elevator to predict possible breakdowns and optimize the performance. So in this case, we are interested in the acceleration of the elevator, because this would help us derive its position and speed, which is enough for the analysis that we want to perform. So in this case, we are focusing on simulating the acceleration of the elevator with the simulation. So what is this system? So for the digital twin, we are using Elevate, which is a commercial simulator that accurately replicates the elevator acceleration based on the specifications. And we also have the physical twin. What is the physical twin? Well, I spent like a couple of hours or even a lot of hours on an elevator just with an accelerometer, taking the traces for the experiments, and that would be it. So in this example, the one that we are gonna use as a running example during the talk, the elevator moves from the 4th floor to the ground floor and then goes back up. So the first two curves represent the negative acceleration as the elevator moves down, and then we have the same acceleration in the opposite direction to stop the elevator in each time, and the same pattern to go back up. So how do we compare the similarity between both trajectories? So I know that there are other methods in the literature, like those from the simulation field, that compare trajectories using probability distributions to describe the system behavior. And they group the data and base the comparisons on these distributions. But our approach stands out because we compare the raw data directly, without any pre-processing or treatment. And how do we do this? Well, our approach is inspired by sequence alignment algorithms like BLAST and Needleman-Bunch, which are widely used in bioinformatics to measure how similar nucleotide sequences are. These algorithms return a score that indicates the level of similarity between sequences, which makes it possible to search for closest matches in a database. That's what BLAST is used for. And And this is typically used to identify nucleotide sequence in such databases. Well, the potential of this algorithm in comparison with the literature is the ability to handle gaps and mismatches and making these alignments much more flexible. For example, in this first one, you can see here a gap, and this is signifying that one character is missing. And if we go to the second alignment, we can see 3 mismatches. These mismatches point 3 characters that are different between the first and the second sequence. And this flexibility in general help us better understand where the sequences differ. So how can we adapt this to our numerical problem? Because we could have traces with also characters or even enumerated values, but how can we apply this approach to numerical? And well, we do this by modeling our problems as sequences of discrete elements that would be comparable. And in this case, we divide the execution in snapshots, which describe the state of the system at a specific moment. And these snapshots must be defined at the correct level of abstraction. As we said before, we are only interested in the movement and dynamics. The acceleration is enough, and this is the level of abstraction of the snapshots. And the full behavior will be described as sequences of snapshots ordered by the timestamp. Each snapshot will represent a set of properties at a specific point in time, just in general. In this case, we only have the acceleration, but if we had more properties of interest of the system, we could have more values. We will have examples of this later in the talk with other systems. So once we have the state of the system represented over time as discrete values, how do we compare these snapshots? So unlike nucleotide sequences, where A is clearly an A, when we have numerical values, is kind of trickier, because we would need a threshold to decide whether 2 snapshots are similar enough to be considered equivalent. And this is why we establish a threshold named maximum acceptable distance, which will be the MAD. And how do we determine this value? Well, when we looked at the acceleration of the elevator, experiments showed that the ideal threshold was around 2 or 3 times the measurement's accuracy. So in this case, the accelerometer that we used to take the traces was 0.05 of accuracy. So the MAD in this case will be 0.15 for all the alignments that we are going to show. And this pattern also helped for the other systems that we tried with this approach. And now that we have the comparison function, to properly align the traces, the algorithm maximizes the similarity score obtained during the alignment. The algorithm is basically a dynamic programming algorithm, and the objective function is maximizing the score of the pairs. In the original Needleman-Bunch algorithm and in our experiments, we found that the most effective scoring scheme was to use a range of value between 0 and 1 for matches. The more similar that the snapshots are, the closer to 1. We assign 0 to mismatches and -1 for gaps. And for matches, as I said, the score gets the closer to 1 when the smaller the difference between the traces. And with this setup, the algorithm prioritizes mismatches over gaps, only inserting gaps when it's absolutely necessary. Because what happens if we do it the other way around? It happens like this. So instead of having just 3 mismatches, notifying that there are 3 elements that are different and 2 gaps, indicating that we have 2 elements that are not present in the other trace, in this case, because sequence 1 is shorter than the second, we had 6 gaps, telling that we have 3 differences, but we don't know if, because they are missing or just because they are different. There's no other way of checking this. So we found out that the first score scheme was more useful. So let's start with the part that I like the most. I I show you some of the details of how the algorithm is implemented, just so that you follow me when I will tell you about the optimizations of the original algorithms. But now let's dive onto the alignments. So this is the alignment that we get when we apply the original Needleman-Bunch algorithm with the score scheme that I told you and the comparison function. But if we take a closer look into this alignment, we see that it is not quite right. So some of the curves have clearly counterparts in the other trace, but these aren't aligned. And you could say that this is because they are over the map. So they are not faithful enough, they shouldn't be aligned. But I can assure that they are not the case. The difference is within the math range, so they should be aligned. So instead, we see that the most of the zero acceleration values are paired with the similar points on the other trace, leaving aside these parts that could be more interesting. We are interested in the acceleration pattern rather than the stable behavior. The issue is that these zero acceleration areas return a higher score because these are noise in value close to zero and compared to zero values. So this just gives almost zero. So the reward is 1. So the algorithm tries to include as many of these pairs as possible to maximize the score. So taking some inspiration from BLAST, we decided to mask these regions. In BLAST, there are some nucleotides that are common across many nucleotide sequences. So they are not really useful when you are trying to search for similarities in the database because you will get a lot of match because of these common sequences. So in this case, we do the same. This provides a lot of rewards. So somehow we reduce the weight of these areas so that the algorithm can focus on the other curves. So applying this masking, we get this alignment, which looks better because we already have all the interesting curves aligned. But even though we could make this even better, because right at the start, if we focus on these few elements, we can see that there is some alternation. Even though the behavior is the same, we can see that there are some matches alternating with gaps or mismatches. And why does this happen? The algorithm, they probably provide similar scores to the algorithm, and given that it gives you the same reward to include a gap than to include a longer gap, the algorithm just alternates these values. But this is not ideal because it makes harder to detect delays, and you cannot see if this is actually a delay or just some stuttering. So this is why we include another technique for BLAST, which is a fine gap, and which consists on modifying the scoring scheme to provide to have a higher cost for opening a gap than continuing a gap. So the algorithm, instead of alternating gaps with matches, decides to just have a longer gap. And with this, we can see that we had no stuttering, just a bigger gap on the beginning because the behavior of the physical twin starts later than the digital twin. So with these two optimizations, we can already analyze the full trace and see that the difference between the traces was just a few gaps at the beginning because the physical twin movement starts later. And we can see also some a few gaps between when the elevator decides to move again. The digital elevator moves later than the physical twin, so we have another delay there that is the second group of gaps. And finally, we have two sets of mismatches in red. These two sets of mismatches are pointing to an anomaly or a discrepancy between the two traces. But this discrepancy, which is this small acceleration, is not actually an anomaly, but is a feature of the actual elevator that improves the user experience. So when you reach a floor, you have an extra acceleration to smooth out the stop. So now that we have the alignment, we pinpoint the difference. How can we quantify fidelity? Because you can see the difference between the traces, but you want to actually compare models to see which one is better, for example. Well, for that, we have three fidelity metrics, which is the percentage of match snapshots, which tell you which one, how many snapshots are within the match range in the alignment. Then we have the fetched distance, which actually tell us the similarity between the trajectories. The fetched distance is actually calculated, well, it's actually explained as if you have a dog, well, you have the two trajectories. One of the trajectories is the dog and the other is the owner. So the fetched distance is the minimum reach that you need to perform those two trajectories. And then we have the Euclidean distance, which is the average distance of the match snapshots. So we have somehow a maximum distance and some average distance. Given these fidelity metrics, we established some fidelity indicators that could help the users tell if the alignments are good or are bad. And this should be tailored by the user, but this is like some general guidelines to help someone that is starting with the tool. So if the percentage of match snapshots is below 90%, it means that there is no faithful behavior, and the distance metrics are generally not relevant because we have not enough matches for these distances to be relevant to assess the behavior of the system in general. And if the percentage of match snapshots is between 90 and 95%, the alignment is also not good, but we could consider the distance metrics when we want to compare with another model. And if the percentage of match snapshots is over 95, we can consider that it's a good alignment, and we could use this alignment to compare between models. And for example, this is an example on how to use the metric for comparing. So the first alignment is the one that we saw before, and the second alignment is a different measurement in the same elevator. So in this second measurement, we can see that the delays between the movements of the elevators are not as big. So we have an increase in the percentage of match snapshots. That is why in this case, it was only the delay, but the behavior in general is faithful. So as long as we remove the delays, we get a better percentage of match snapshots. So now let's dive in to analyze other systems. And we have three systems, and the first one is an incubator that we will use to exemplify how to compare models. The second one is a robotic arm to analyze snapshots with multiple parameters. And the third one is a robotic car because it has not only many parameters, but of many types. In this case, this is an incubator from the Aarhus University. Claudio Gomez provided that with the snapshots and with all the traces. And we want to thank them for their work of him and his team. In this case, they had two models, one with two parameters that was much more cheaper, and it was computationally not as expensive, I mean. And we also had a 4-parameter model that was supposed to be more precise. So we had also two scenarios. In this first one, the incubator spent 3 seconds heating and then stopped for 2 seconds and then waited until it decided if the range of the temperature was okay, then it continued heating, and if it was almost at the limit, because it had to be within a range, then it stopped heating instead of continuing with the loop. So in this case, the heating and cooling was fast, but this was not good for both models because they struggle with the transitions between heating and cooling, and also between cooling and heating. This is the most difficult part for both models. But if we go to the second example, in which we increase the periods between heating and just stop heating to 30 seconds and 20 seconds, we can see some difference. For example, in the case of the 2 parameters models, this longer period in which the incubator is not heating, these 20 seconds, heavily affects the behavior of the 2 parameter models, which started to cool down, and even when in the real system, it doesn't cool down at all in 20 seconds. So this generates a sawtooth pattern that heavily impacts fidelity. But in the case of the 4-parameter model, and actually this change of pattern helps in the fidelity. And we can see some struggle in the transitions, but in general, it's pretty good. So we get almost 97% of match snapshots. And with this, we can conclude that the 4-parameter model is more useful than the 2-parameter models when we have longer heating and cooling gaps, but we can see that it's not good when we are dealing with faster transitions. And then we have our second example. This is a robotic arm. And in this case, this example we had as in the previous example and in the elevator, we had a digital twin that should behave as the physical one. In this case, we focus on that on the other way around. We had an engineering model and we want the physical arm to work as our engineering model, just to check if the Arduino Brachio is enough or we need a more expensive robotic arm. And in contrast to the previous examples, in this case, we have snapshots of 3 values, and which is the X, Y, and Z position of the point of the gripper. So in this case, we have a scenario in which the robot's arm goes down, grabs an object, goes up, moves, and then drops the object. This is what we see here. And we can already see the differences because the physical robotic arm is not able to move as fast as the model is telling to. For example, in around 10K seconds, we can see how in the middle there is a big group of gaps because it's not able to proceed as fast as the digital one. But if we go to another scenario in which the requirement is to move slower, we can already see how this is more adequate, and we get over 90% of match snapshots. And finally, we have the example of the Lego Mindstorms car. This is a toy car, and all the traces are synthetic, but this is just for illustration purposes because this is a system in which we have not only numerical values, but we also have booleans and we also have enumerates. And in this case, we can see how it affects the alignment to have a boolean value with some discrepancies. And these alignments become more strict because as long as there is one attribute that is not faithful enough, we include a gap in all the attributes. But this also helps to detect any discrepancy in any of the sensors. So this is our proposal, and we wanted to compare our proposal with other well-known alignment algorithm of the literature, which is dynamic time warping that many of you may know, and if not, I will provide you a brief summary. So dynamic time warping is an algorithm that is used to measure the similarity between 2 time series. And the point is that they may vary in speed, but it still helps you to measure the similarity. And in contrast to our algorithm, dynamic time warping aligns one snapshot to many snapshots of the other trace. So as we see in the animation, and if we have some warped time, it may mean that one state may represent many. This has many advantages as that we can align warping sequences, but it also has some downsides. For example, in dynamic time warping doesn't consider gaps and mismatches. So even if the 2 snapshots are way farther apart, it will keep aligning them. And this means that the alignment that dynamic time warping is doing, and it won't point you to any discrepancy, or it won't help you to reason about which parts of the alignments are different. It just provides a similarity value that tells you if 2 trajectories are closer to the other. But these also have some problems because dynamic time warping suffers from overstretching or overcondensing. What does that mean? It means that it tends to overuse certain points in order to maximize the similarity value. For example, in this first alignment, and if one snapshot is aligned to 28% of the snapshots of the other trace, just to maximize or to minimize this measurement at the most. And this leads you to provide you even a similarity measurement that may not be reliable, because the alignment is not aligning what is similar, is just overusing some parameters to minimize. And this would be all. So I provided you with some guidelines about what fidelity is and how you can increase or reduce the fidelity of a system. And I also presented you our tool. And what is next for the future. So we want to consider uncertainty in the comparisons. We want to include uncertain values in the comparison function. We want to evaluate fidelity at runtime. For the ones of you that were at the EDT.Conf, you already know that we are working on this with the sliding windows. And we want to perform some automatic diagnosis of the discrepancies. As I said, we can detect delays and anomalies, and we want to give some feedback to the user in an automatic way about what are the discrepancies in the alignment. And finally, we want to try with solo digital twins. And this is when it comes back to you. So I know that many of you may be working on digital twins. And if you have a digital twin, you will probably need some validation. So if you want to try how faithful your system is against your replica, send me an email. We can chat. And also, if you don't want to send me an email but want to try the tool, is publicly available on GitHub, and you can see from the QR code. So if you have any questions or any comments, please feel free to ask.
Thank you very much, Paula, for this great presentation. It's really great. Thank you very much.
Thank you.
I will stop recording, but we still